Okay, so chapter 12 gets us over into the analysis of variance. Our objectives, if I can bring them up here, apply the F distribution to a test hypothesis that two population variances are equal. So we want to apply an F test. Use ANOVA to test a hypothesis that three or more population means are equal. We'll look at ANOVA. And use confidence intervals to test and interpret differences between pairs of population means. All right, so 3 objectives. So let's first apply some meaning behind these objectives. How would you take the floor here? How would you define, tell me, how would you define an F test? First, when are we going to use it?
It's used to test whether two samples are from a population have equal variance.
Used to test a hypothesis of equal population variances. So the F test is going to be used to test a hypothesis of equal population variances. We can use it to simultaneously test a hypothesis that several population means are equal. Now, the simultaneous comparison of several population means is called the analysis of variance, or ANOVA. So we're going to use this to test the hypothesis, and we're going to use this to compare several population means. One thing that I will point out that with ANOVA, it will tell us whether or not these population means are equal. However, it's going to have a hard time. One shortcoming of it is that it's going to not tell us which of the items we're observing, which of those are unequal. It will just show us that one of them is unequal.
Okay.
All right, so we'll start looking at some of the more advanced testing if we wanted to narrow down what that is. So let's look at a problem. So from chapter 12, let's look at problem 1 on page 385. Okay, what is the critical F value for a sample of 6 observations in the numerator and 4 in the denominator? Use a two-tailed test and a 0.10 significance level.
Okay.
All right, where do we begin?
We have to find the degree of freedom in the numerator and the denominator.
How many degrees of freedom are we going to have in the numerator?
There's going to be 5.
So 5 degrees of freedom in the numerator.
And then there is 3 in the denominator.
3 in the denominator. So let's flip back to appendix B6 and see what we uncover.
6, 0. This doesn't have 0.10 on it. Is this supposed to be for 0.05? Or is it just an example?
So what are the F value for a sample of 6 observations in the numerator
Mm-hmm.
and 4 in the denominator? Using the two-tailed test at 0.10 significant level.
So if we, if 5 is the numerator and 3 is the denominator, then it's gonna be 9.01.
Okay, so let's flip back. We're gonna have degrees of freedom, 5 in the numerator,
Mm-hmm.
and how many?
3.
3.
And that's
So looking at appendix, is it B6?
B6A,
So what do you get?
9.01.
9.01. Interpret this.
Okay.
What's this telling you?
Yeah, I'm not sure.
Let's look at this.
I'll look and see what. Okay.
So we're going to put the formula up here.
Mm-hmm.
Well, first you have to interpret what you were looking at from your decision rule.
Mm-hmm.
Okay, now we've not applied any of our 6-step hypothesis testing yet.
Right.
We do notice we have applied an F test here.
Mm-hmm.
Now let's set this up and see how we would be determining this. Is it would be telling us if there was some difference in variation.
Okay. So that would be what we would use in our hypothesis, in our null hypothesis.
We will set up our 6-step hypothesis testing
Okay.
model. We would be applying that model.
Okay.
And let's try to look at one where we are. But depending on, we're going to interpret this by saying that there could be some variation depending on what our decision rule was.
Okay.
All right, so going back to the textbook. We can look at here you go. Let's look at problem 3.
Okay.
So problem 3. I got a second to dry. We're going to say the following hypotheses are given. Hypotheses are given. What's the null hypothesis? The variance of the first observation is less than or equal to the second population.
Oh, are you looking at 4?
I'm looking at
3 is equal to.
3. So we want to say it's equal to. Okay. So our alternate hypothesis it gives us is we are not equal. So the remember, if this null proves to be false, what must we accept? It says that a random sample of 8, so over here we know that. So n is equal to 8. A random sample of 8 observations from the first population resulted in a standard deviation of 10. And the second population resulted in a standard deviation of 7. At the 0.02 significance level, is there a difference in the variation of the two populations?
You left out the 6 observations from the second population.
I left out what?
The 6 observations, the random sample of 6 observations from the second population.
Get back over. So N1 is 8,
Mm-hmm.
and we take 6 from the second,
Yeah.
right?
Yeah.
6?
6.
Okay. So the sample size, so we take a sample of size of 8 shows us that the standard deviation is 10. And the second population size is 6, and the standard deviation is 7. Testing at the 0.02 level of significance, we want to know, is there a difference in the variation of the two populations? All right, where do we start?
We're gonna have to.
Let's go with, let's apply this using our 6th step. All right, so we pretty much applied the first step here.
Okay.
What's step 2 in our 6-step process?
Sorry. Select the level of significance.
Correct. So the level of significance we've been given is 0.02. What's the 3rd step?
Appropriate test statistic.
All right, the appropriate test statistic. What are we going to apply?
F test.
All right, so we are testing. When do we use the F test?
We're comparing to population samples.
Think about that. 2 population samples. Contradicting here.
Yeah.
Now, we want to use the F test when we want to compare
Equal variance.
Okay, what are we studying here? Variances.
Mm-hmm.
So when do we want to use the F? To test a hypothesis of equal population variances. So remember, we are trying to see if there's a difference in the variances between these two populations. Therefore, we're going to order the F test. Okay, what's step number 4?
Formulate decision rule.
Formulate the decision rule. All right, so let's start here. The decision rule is what?
We don't know what it is yet. Oh, Amber Alert's going on. Madison.
We have an Amber Alert. Okay. It's the second one today here in Indiana.
I know, I saw that. There was one up north.
Up north, from the state. All right, so let's formulate our decision rule.
So we have to figure out our degrees of freedom first.
Not right now, we're not going to move into testing yet.
Okay.
But right now, we're formulating the decision rule. So what are we trying to determine here? What's it asking us to determine?
If there's a difference in the variance.
All right, so we are going to reject the null hypothesis if what?
If it's greater than?
If F is greater than what? Now remember, our formula for computing F is what?
S2. And then it's S2 over 1 and then S2 over 2.
Okay. So the standard deviations in the first was 10, and it's 7. And we're going to square both of those. So what does F equal?
$2.041.
2.041. All right, actually what we did here was we just computed.
Okay.
Now our decision rule, we're going to reject the null hypothesis is F is greater than 10.
Okay, so
10.5.
where do we get the 10.5 from?
Go right back. First sample size, or excuse me, first population of 8, second of 6.
Okay.
Degrees of freedom are going to be equal to 7 and 5.
Okay. So on the decision rule, you're always trying to figure out the degree of freedom. And that's what your F is gonna, or
Now,
whatever.
we're not trying to figure out degrees of freedom.
Mhm.
Remember, to come up with the degrees of freedom, we subtract 1.
Right. Okay. But you're trying to figure out the number that F needs to be greater than or less than. and that's.
You're going to apply, when trying to come up with your decision rule, you are going to apply and coming up with the value of, let's just say you're going to apply the degrees of freedom, but we're not solving for them.
Okay.
Step 5 would be where we compute, which is what we just did. And step 6 of our decision rule is always to interpret. So how would we interpret?
That, so we are accepting the,
What's your language here?
okay,
We're not accepting anything.
okay. The F test,
Now look, we do not reject
okay,
the null hypothesis. On our language, in our hypothesis testing, we do not reject it. We don't
Okay.
accept it necessarily.
okay,
We're just saying the evidence here is that we do not reject it.
okay,
Okay, now taking that one step further, there is no difference in the variation of the two populations. There is no difference. Okay. Last thing we want to look at here is applying an ANOVA. So looking at problem 7. And again, let's look at this. When do we want to use ANOVA?
when we're doing several different,
We're applying ANOVA when we want to test what?
different populations
Different population what?
simultaneously.
What about the population do you want to test? And specifically, how many?
You're gonna test like the same. Here's my notes. You're gonna compare several population means. It's a simultaneous comparison of several population
Used to
means.
simultaneously test a hypothesis that several population means are equal.
If they're equal.
So specifically, you want to test if, remember, population means, so you want to simultaneously test whether or not multiple population means, and I would define multiple as more than three or more, population means are equal. So let's flip over to page 394. The following are four observations. The following are four observations collected, and I'm looking at problem 7.
Mhm.
The following are four observations collected from each of 3 medical treatments. Test the hypothesis that the treatment means are equal. Use the 0.05 level of significance. So step 1, applying our 6-step test.
Mhm.
We're to state the null and alternate hypothesis. All right, well, we're asked test the hypothesis that the treatment means are equal. So what's the null hypothesis?
It's gonna be that they're gonna be equal.
All right, so we're gonna say that the population, the first population mean,
Is equal to the second.
and that is equal to the third.
Okay.
Now, in step 2, what is the decision rule? But now let's all the way go back, because I'm gonna get you in the process of going through this 6 steps.
And we have to do don't we have to do the alternate on that too, though?
Oh, well, yeah, so what would our alternate be?
That they're not equal.
Good catch. All right. Alternate hypothesis is that the mean of the first population is not equal to the second, and it is not equal to the third.
Okay.
Now remember, this is going to tell us simply that the 3 population means are not equal.
Okay.
It is not going to tell us which of the 3 are not equal.
Okay.
Again, that will come in a more advanced class.
Good.
Right now, we're just testing to see if they are equal or not. All right, so what's step 2 in our 6-step process?
The level of significance.
The level of significance.
Which is 0.05.
0.05. Step 3.
The test statistic is going to be the F test.
We want to look at an F test, and 4 is our decision rule. All right, so what's our decision rule?
Well, would we add all the treatments for each one and figure out? No. Subtract 1 from 4 on each one of them to get the.
This is our 3rd example, so I'm going to let you take over.
Okay. So let's see.
So our decision rule. We're going to reject the null hypothesis if what?
If F is greater
If
than.
F is greater than what?
That is what I have problems with. How to figure. I mean.
You're going to figure it just as we did prior. You're going to use the appendix in the back.
But you have 3.
But you have 3, so I'm putting a curve on you.
I know. Okay.
What's the text tell you?
All right. We're on step 4, so. It says degrees of freedom in the numerator is going to be k minus 1 equals 4 minus 1 equals 3.
All right, so step 4, to determine the decision rule, we need the critical value. The critical value for the F statistic is found in appendix B6 of your test. Critical values for the 0.05 significance level are found on the first page, and the 0.01 significance level is found on the second page. Now, before we use this table, we need to know the degrees of freedom in the numerator and the denominator.
Okay.
All right. The degrees of freedom in the numerator are equal to what?
The number of treatments.
Number of treatments. And we're going to designate this as K1.
So 4 is gonna be,
So we're gonna say that K1 minus 1. So we're gonna say K1 minus 1. And then the degrees of freedom in the denominator are the total number of observations n minus the number of treatments. Okay, so let's look here. Equal to the number of treatments designated as K minus 1. So in the numerator, we have K, let's just say K minus 1 is equal to what?
is it equal to
4
4
minus 1
minus 1?
is equal to 3.
Okay.
Now, degrees of freedom in the denominator are equal to what?
N minus K. And N is the total number of observations.
All right, so for the
Minus
denominator, the number of observations n minus k. Okay, so how many number of observations do we have?
4.
And what do we start with? N.
We add them together.
Okay, how many?
We're just working on one.
You're working on the denominator.
Okay. So T1 is going to be 33. Or do we have to add all of them together?
Refer to the text.
Yep.
Refer to that problem.
This gives you what the 20, there's
So
22.
correct. So apply this
Mm-hmm.
to what we're trying to solve on the text.
Okay.
You just defined K here.
Mm-hmm.
So what's N?
It's going to be the total number of
Observations.
observations.
How many observations do we have?
12. Okay.
So now, let's formulate our decision rule.
It's going to be 3.86. So the decision rule is going to be reject the null hypothesis if the F solution is greater than.
Okay, so the correction. K minus 1. We're going to define K as a number of treatments that we're testing. Okay, so within each treatment we have 3. For the degrees of freedom, we're taking 3 minus 1 or 2.
Mhm.
And then the degrees for the freedom for the denominator are going to be equal to n minus k, which is equal to 12 minus 3, which gives us 2 over 9. Now, looking at our appendix, this gives us 4.26.
Mhm.
So we are going to reject the null hypothesis if F is greater than 4.26. Step 5. We want to compute So let's compute F.
And this is where we have to make our ANOVA table.
Here's where we're gonna make the ANOVA table. So I'm gonna put my ANOVA table. Where can I squeeze it up here? We're gonna build our ANOVA table.
Okay.
So we're gonna take the source. The treatment. Air. And then the total. All right, help me define this. SS, what am I referring to?
Is the sum of squares.
Sum of squares. So what are the sum of the squares for the treatment?
That's going to be x minus.
I'm going to give it to you, 62.17. And how did I come up with that?
Says determine the values by obtaining SS total and SSE.
Okay, sum of squares for the source.
Mm-hmm.
So we're going to do the sum of squares for the treatment and sum of squares of errors. So for the treatment was 62.17. How did we get that?
For the treatment. SSE. The SS total.
No. SS total is going to be the sum of squares for the treatments added to the sum of squares for the error. So how do we get up here first? For the sake of time, I'm going to give you the sum of square of the errors is 12.75. But what are degrees of freedom? So remember, you'll need to come back and
Figure those.
look at this.
Yep.
Our degrees of freedom are 2 and 9.
Yep.
What's next?
Mean square.
What's the mean squared?
It's going to be the SST divided by K minus 1, which is going to be the sum of squares divided by the degrees of freedom.
.08 and 1.42. And then finally, what is F?
F is going to be the mean squared treatments divided by the mean squared error.
We'll divide that.
22.887. Or 21.887, sorry. So
31.08 divided by 1.402. We get 21.94.
Yep.
All All right, so let's go back and formulate. We're going to reject the null hypothesis if f is greater than 4.26. We just computed that f is equal to 21.94. Step 6, interpret the results.
We're not gonna accept the null hypothesis.
Well, we're going to reject the null hypothesis because f is greater than 4.26. Now, we can say when we reject it that not all population means are equal.
Because one of them has to be,
But we just know that of these three, the three are not equal.
Yeah.
So we are rejecting this.